A simple equation for predicting the punching shear capacity of normal and high-strength concrete flat plates. Introduction. Flat plate construction is very common in parking, office, and apartment buildings. Exclusion of the beams, drop panels, or column capitals in the structural system optimizes the story height, formwork, labor, construction time, and the interior space of the building. This makes flat plate construction a very desirable structural system in view of economy, construction, and architectural desires. However, from structural point of view, supporting a relatively thin plate directly on a column is significantly problematic due to the structural discontinuity. 1. Punching shear failure disasters have occurred several times in the last decades. This type of failure is extremely dangerous and should be prevented. In 1995, June 30, a 5-story Sampoong department store in South Korea collapsed due to this sudden brittle failure, where more than 500 people were killed and nearly 1,000 were injured too. Also, Piper's Row multi-story car park, which was built in 1965, collapsed during the night of 1997 March 20. Initial reports identified some of the factors which contributed to cause punching shear failure, which is developed into a progressive collapse. 3. There are significant variations in the approaches used to assess shear resistance of reinforced concrete slab column connections in the current major codes. Generally, all design codes adopt the simple shear on certain critical perimeter approach and involve only the most important parameters. The critical section for checking punching shear is usually situated a distance between 0.5 to 2.0 times the effective depth, d, from the edge of the loaded area. 0.5 d for ACI, CSA, IS 456 and 2d in EC2. The other important difference amongst codes is in the way they represent the effect of concrete compressive strength, FC, on punching shear capacity. Generally, these codes express this effect in terms of FC, N, where N varies from 1/2 in the ACI code to 1/3 in the European code. The further complication is the definition of the concrete compressive strength. The ACI and CSA codes use specified concrete strength FC, while the European and Indian codes use characteristic strength FCK. Punching shear provisions of current major codes are illustrated in Table 4. The main purpose of this study was to propose a new simple punching shear equation for both normal strength concrete, NSC, and also for high strength concrete, HSC, flat plates, and to compare the proposed equation with the shear strength provisions of ACI 318-14.5, Eurocode 2.6, CSA 823.3-14.7, IS 456-2008 for interior slab column connections without shear reinforcement. Research significance. Punching shear is a very important issue, especially in flat plate slabs. Errors in predicting the punching shear have shown to lead to catastrophic failure. 9. Different codes have discussed the punching shear provisions with great importance. In recent years, the use of high-strength concrete, HSC, is becoming more and more popular. Increase uses of HSC is faster than the development of appropriate design code and recommendations. Several recent studies showed that HSC have different characteristics than NSC. As the use of HSC is becoming more popular, the importance of research on punching shear provisions for HSC is increased. Even for NSC, to calculate the punching shear capacity according to most of the major codes, it is required to use several equations and need to deal with various factors. Thus, a simple equation is needed to predict the punching shear for both the NSC and HSC. Although some researchers including Rankin, 1987, 2003, Sharif and Dilger, 1996, Gardner and Shao, 1996, El Gamal and Benmo Crane, 2004, Ali S. Abdul Jabbar et al., 2012, El Sanadi, H.M., Al-Saloom, Y.A. and Al-Said, S.H., 2013, proposed their own equations to predict punching shear as shown in Table 1 4,10,11,19. However, These equations are not studied in this research. Data collection. Punching shear tests can be done on either a multi-panel structure or on isolated slab-column connections. Multi-panel tests are time-consuming, expensive, and it is difficult to determine experimentally the shear and moments applied in individual connections. Isolated slab-column connection tests have the problem that the boundary conditions may not equals to 1. It is generally accepted that the punching shear capacity of slab-column connections results from concrete contribution and the contribution from shear reinforcement, if present. However, this study is limited for symmetrical flat slabs without shear reinforcement and connected to square or circular columns, which means the aspect ratio is neglected and all other factors is taken to 1.0 for comparison reasons as noted before. So, to make the comparisons easier, the provisions for the nominal concrete shear capacity Vc can be summarized in Table 4. EVU's 10 statistic program is used to get the equation to predict the punching shear strength of interior column slab connection of HSC flat plates. HSC specimens from literature conducted by different researcher 13, 14, 15, 16, 17, 18, 19 were selected for the regression analysis given earlier in Table 2. Investigations showed that the main variables affecting punching shear strength are concrete compressive strength, FC, flexural reinforcement ratio, average effective depth, D, column geometry, critical perimeter B0, 20. These declared 4 variables have the most significant effect on flat plates without shear reinforcement. All comparisons in this study are with the results from tests on isolated specimens. Flat plates are widely used for floor construction in multi-story buildings. As such, a significant amount of experimental research work has been done on the punching shear failure of concrete flat plates. A review of the literature revealed that only a few experimental studies are available on punching shear strength of high-strength slabs. The specimens data was collected from the previous test results of isolated specimens conducted by Hallgren and Kainanen, 1996, 13, Merzouk and Hussein, 1991, 14, Tom Azraz, 1993, 15, Osman et al., 2000. 16, Ramdane, 1996, 17, Osden et al., 2006, 18, Susanto et al., 2018, 19 with a total number of 38 specimens. These selected specimen samples for this study have compressive strength ranging between 70 to 119 MPa. The reinforcement ratios were between 0.33 to 2.62%. The effective depth ranged between 70 to 275 mm. Table 2 presents details of HSC data. A large number of normal strength concrete specimens, 243 specimen, test data are collected from literature, Susanto et al., 2018, 19 where these data from 1956 to 2012. Table 3 presenting some of the details of NSC data from 243 samples. Analysis of data. In this study, for the purpose of comparing code provisions, safety factors have been removed from the equations. It might be important to note that this comparison is held between code provisions of interior circular or square columns of C1/C2 ratio, where Vc equals predicted nominal punching shear stress, N. Fc equals concrete compressive strength, MPa. D equals average effective depth, mm. Equals flexural reinforcement ratio, %. B0 equals critical perimeter at distance D/2 from column face. B0 equals 4, C plus D, 4 square column. And, C and D, 4 circular column. C equals column diameter or width, mm. The above equation has R2 equals 0.98. It should be illustrated that in the proposed equation, the critical section was assumed to be at a distance of D/2 from the column face because this value has been used to define the critical section in the ACI code since the 1960s. Therefore, the critical perimeter, B0, is equal to 4, C and D, 4 square columns and, C and D, 4 circular. Columns. It is important to emphasize that the suggested equation was concluded using punching shear strength testing database with specific physical and geometrical limits of the following: circular and rectangular columns with C1/C2 ratio equals 2. Therefore, this proposed equation should be updated by the same expert software program EVAS 10 for its application to wide range beyond those mentioned here once testing database on HSC flat plates become available. The above suggested formula of equation was utilized to assess the concrete punching shear capacity for the 38 HSC specimens, and the ratios of the experimental to predicted punching shear capacity are then calculated and plotted as displayed in Figure 1. Comparison between experimental versus predicted by the proposed equation for high-strength concrete, HSC, specimens is presented in the Figure 1. Although, the basis in deriving the proposed equation was estimating the punching shear for high-strength concrete flat plates, we might extrapolate it for use with normal or low-strength concrete, NSC. Therefore, to evaluate and assess the applicability of this proposed equation for NSC, a sample of different slabs tested by different researchers with compressive strength less than 69 MPa were used. The prediction of shear strength for normal strength concrete, NSC, specimens by proposed equation and different codes are calculated, and the means, standard deviations, and coefficients of variation are given in Table 6. The statistic parameters, mean, standard deviation and the coefficient of variation were used for comparing with ACI, EC2, CSA, is provisions in Table 6. Figure 3 shows a comparison between experimental versus predicted by the proposed equation for normal strength concrete, NSC, specimens. Also in Figure 4 shows a comparison between experimental versus predicted by different codes and the proposed equation for normal strength concrete, NSC, specimens. 281 existing published data for normal and high-strength concrete specimens is used to evaluate the accuracies and safety of the ACI 318-14, Eurocode 2, CSA 23.3-14 is 456, and proposed equation for punching shear. Table 7 shows, mean, standard deviation and coefficient of variation, FOT. The comparison of the proposed equation and ACI, Eurocode 2, CSA, and is 456. In all cases, test was conducted on square or circular slabs supported by column stubs or loading plates. Figure 5 shows a comparison between experimental versus predicted by the proposed equation for normal and high-strength concrete, NSC and HSC, specimens. Also in Figure 6 shows a comparison between experimental versus predicted by different codes and the proposed equation for normal and high-strength concrete, NSC and HSC, specimens. Discussion. According to above analysis based on the available data of specimens from different experimental studies, the relation between the variables and the punching shear strength of interior slab column connection of HSC flat plates could be defined as below. Compared with the given provisions of major codes, ACI, EC2, CSA, this proposed formula based on regression analysis gives good correlation with test results. Therefore, the new proposed equation reasonably shows that the punching shear strength in HSC flat plates is proportional to the square root compressive strength, but it also shows that the influence of the flexural reinforcement ratio is proportional to the cubic root. On the other hand, it was found that the punching strength is proportional to the effective depth multiplied by the critical perimeter, which is in accordance with the definition on the ACI code. In case, using HSC, the ACI 318-14 shows the most conservative and scatter results among other design codes, as evidenced by the highest mean of 1.30 and standard deviation of 0.27. While EC2 prediction shows the least difference to the experimental values with the lowest mean of 1.01 and least scatter with a standard deviation of 0.11. On the other hand, proposed equation is better than ACI code and close to CSA 23.3-14 and is 456:2000. In case, Using NSC, the ACI 318-14 shows the most conservative and scatter results among other design codes, as evidenced by the highest mean of 1.40 and standard deviation of 0.30. While EC2 prediction shows the least difference to the experimental values with the lowest mean of 1.01 and least scatter with a standard deviation of 0.21. On the other hand, proposed equation is conservative, similar to ACI code with mean of 1.37 and standard deviation of 0.21. Canadian and Indian code with mean 1.22, 1.23 and standard deviation of 0.26, 0.26 respectively. In case, using NSC and HSC together, the ACI 318-14 shows the most conservative and scatter results among other design codes, as evidenced by the highest mean of 1.39 and standard deviation of 0.29. While EC2 prediction shows the least difference to the experimental values with the lowest mean of 1.01 and least scatter with a standard deviation of 0.20. On the other hand, proposed is conservative, similar to ACI code with mean of 1.35 and standard deviation of 0.22. Canadian and Indian code with mean 1.21, 1.22 and standard deviation of 0.26, 0.26 respectively. The statistical analysis is summarized in Table 7. It must be noted that the ACI 318-14 places the upper limit of by 8.33 MPa, which means it is limited to a concrete with a compressive strength of about 6.9 MPa. This limitation in the American code is due to the fact that these provision developed mostly from tests on low and normal strength concrete flat plates. Therefore, this study uses 70 MPa or more as a HSC flat plate specimens. From the previous summary, it is clear that the European Design Code consider the influence of the flexural reinforcement on the punching capacity of slab-column connections either. However, the proposed design equation is limited to flat plates with depth not more than 300 mm and concrete compressive strength below 120 MPa. For slabs exceeding these limits, experimental validation is required. The proposed equation is only meant for typical interior columns. Moreover, the validity of different code approaches to predict the punching shear strength were checked and compared with the new presented formula. It is found that the new proposed equation can be used for high strength or normal strength or both of them with a reasonable accuracy. This equation for all strength levels studied gave conservative results compared to ACI 318, EC2, CSA and IS 456 codes. Generally, the investigations show that the punching shear predictions of ACI 318-14 is conservative and with large scatter compared with Euro 02 code formula, which is more accurate and with smaller coefficients of variation. The CSA and the IS 456 codes seem to be in good correlation with experimental results. The provisions of North American codes ACI 318-14, CSA 23.3-14, which are based on same expression, do not include the influence of flexural reinforcement. The proposed equation, which is based on regression analysis by using an expert software program, depends on results of specimens from different studies and includes the influence of flexural reinforcement ratio. Conclusions. This parametric study showed that the significant parameters that primarily affect the punching shear behavior of slab-column connection of flat plates are concrete compressive strength, slab effective depth, flexural reinforcement ratio and critical perimeter. Despite being a simple equation, the new proposed equation includes the main four significant parameters, F, C, D, and B0, can predict the punching shear capacity with a conservative and reasonable accuracy compared with other available design codes. 1. The proposed equation is found proportional to 1/2 the square root of the compressive strength and to the cubic root of the reinforced ratio, and to effective depth, and assumed that the critical perimeter at a distance 0.5 d from the column face as it defined in the ACI 318-14 code. The punching shear strength of plates is a function of the flexural reinforcement ratio, and the investigation shows it is proportional to power 1/3 and a power of 1/2 for Fc. This proposed equation is in good agreement with other code equations, yet it has a very simple form and is valid for a wide range of normal as well as high-strength concrete flat plates. The proposed equation has the following form: